So today is the fourth part of the 10-part tutorial that we are building on the book Nanobrain, the making of an artificial brain made of time crystal. And today in the fourth chapter, we will be discussing uh, primarily fractal mechanics, a new kind of mechanics that we are proposing. Uh, mm, Fractal space-time was introduced in the 1970s, 1980s, and especially Jane Ord, Owen Ord, and then from France, El Nashi from somewhere. Um, there are many legendary scientists who have contributed, but uh, fractal space-time and fractal mechanics both are fundamentally different. So at the outset, I would like to tell you that what are you going to see here is not it's not space-time curvature, and how the space-time curvature would look like. So fractal space-time is about choosing different kind of grids, okay, and how space-time pathways would be, and that intricacy of the path is the was the main concern. But here, as you know, that in the Nanobrain book is a historical adventure towards creating a new kind of science um, where we consider that events in the universe cannot be sequentialized as it was done in the last 300 years in the Western science. So what we used to do, we consider any event that is happening in the nature, we can rewrite it in terms of small bits of pieces of events, all identical events. They could be rearranged and then they can make it. So you can have an infinite thread where you can write events, simple events one after another, and you can recreate the universe. So that is the very fundamental principle behind every single science that you see in physics, chemistry, mathematics, biology, everywhere. We are suggesting, we are not trying to reject that one, but we are suggesting is that events are not, what if the events are not horizontally, sequentially organized one after another? What if the event is there, whatever be the event, uh, if you go inside, you will find some more events, and if you go inside, some more events. So the assembly is within a napa. So it's a vertical journey, not the horizontal one. And it's a topological, geometric, so you cannot split it in terms of threads. When you have this kind of situation, then you need two things very importantly. You need a mechanics, so that you can find out how, if you apply force, how different layers will be interacting. That question was never asked, and that the answer doesn't exist. So the question and answer both would be here in this chapter, and at the same time we will give experimental evidences also. It's not that for the last 15 years of my life I have totally dedicated in understanding this kind of system, and with experiment we verified, then we came to the theory, and then we proposed it. So 2016, first we proposed it, and then in the book we have detailed the summary. But of course, another part of it is that when you try to explain how different imaginary worlds which are existing one inside another are interacting and affecting far distant locations, some other imaginary worlds, you need to build a new kind of algebra. And we are restricting ourselves to 12 to 20 different layers, one inside another. Why 12? Because our while modeling the human brain that we'll describe in chapter 7, and that is will be the seventh video of the tutorial, you will see that there are 12 layers, one inside another, is essential, minimum requirement. Also in the chapter 2 and chapter 3, while going through the book, you must have seen that um, uh, 12 is very important, because 2 into 23, 2 into 3 into 2, 3 into 22, you can nest it in multiple coexisting ways. So 12, that's why, is the first integer. 12 is not the last. 12 and 18, and then maybe 32 into 5 into 3. So in this way, you can compose universes, or if you have a single hardware, you can the information architecture, the time crystal produced by single hardware, could be three different ways. So that is actually the essential necessity to make a conscious machine, because when one piece of hardware produces three different kind of time crystals, then they are projected to infinity. They create an infinite series by phase prime metric and projected to infinity, and from infinity it comes back. When it comes back from infinity, then it returns a topology. So it is essential to build a conscious machine that the projected topology from infinity must be another topology. Then what happens? It enters inside the phase prime metric, and then it goes up, and then an infinite cycle is created, which is the fundamental criterion, one of the fundamental criteria for building a conscious machine. So in this chapter, we basically it has two parts. One, we have to build a mathematics where we will use clocks and to do all kind of mathematics, and then um, uh, 12 different imaginary layers. Why it is different? Why it is so difficult? Because while developing this mathematics, I'm good in mathematics, but not so good. So in the initial days, in the 2014, 2015, I made several mathematicians and requested them for help. It is impossible to get their help. The reason is that when I say that I have imaginary worlds, one inside another 12, then they said that in string theory, the people used 10 imaginary layers, one inside another, that is octonions, and then quaternions, that is 4 imaginary layers, and then they bind them together in a linear fashion. So 4 world, imaginary world, 8 imaginary world, couple them with one wrap factor, and then they try to explain 12-dimensional universe, which is never the reality, which is totally fake, and and very unreal. Why? We will see that in this chapter, because when you go to 12 imaginary layers one side another, you can group the different imaginary layers, and then how one is affecting others in a very unique way. It opens up a new world, a completely new domain of computing. So we have detailed research papers. If you are interested in detailed research papers, always contact me, and you know that I'm always freely available. I have enough time, unlike the great scientists of the world. I will always send you the papers that we have built on this particular topic. So let's get into each figures one by one. So figure 4.1. Figure 4.1, you can see that figure 4.1a. Here we are seeing using geometrical musical language to look at the very well-known quantum mechanical phenomenon. So basically, if you have a new language, suppose in this case, from chapter 2, we have got a new language that is geometric musical language. So we convert every single information in the universe into a geometric shape. So we have 15 geometric shapes and we convert. So the fundamental part of it is that we need a clock or circle, and we need a singularity point. 3 singularity points are there. Singularity points means undefined. So I have taken a lot of time in chapter 2 and chapter 3 to explain what is singularity point. So it's a confusion, and I'm not getting into the philosophical details of it. So if you have a clock and you have 3 singularity points where undefined, where you don't know whether you are inside the clock or outside, whether time is flowing or not. So these are time cycle, right? So in this time cycle, when you encounter three points, then it becomes singularity points. So now that's the basic and only knowledge is required for this particular chapter to go. So wave particle duality, how do you rewrite it in terms of geometric musical language? So you take a circle and you put a dot. The dot is the particle. So particle is moving in a circle. Particle could be a hypothetical elementary particle or subatomic particle, or it could be a packet of energy which is moving, changing its phase in a cyclic manner. So you get a wave because it's a circle, and then you get a particle, both. So wave particle duality, if you want to rewrite it in terms of GML, the best way is to take a circle and put a dot. Now, suppose you are doing the measurement, then what you do? What you got to do is that you will have a dot, which is observer, and a circle, which is the phase cycle, and observer can sit anywhere, wherever it is, that phase observer observes. So if you take a circle and put the observer on its perimeter, then it becomes observed, an observed entity. And then suppose instead of a dot, you have observer with a big clock, and then the thing that you are observing is also its diameter is nearly similar to the big circle. Then it becomes, one of them becomes host, another of them becomes guest. So who will become host and who will become guest, you cannot control. Mm, uh, it actually is automatically decided. For an example, universe is say 15 billion years old. Then what happens is the universe can see you. You can't see the universe because your time cycle is much smaller than the larger circle. Suppose what you want to measure is a dot, and then you are the observer with, say, universe. I'm the universe. I'm the big observer, and I want to observe a human. Then what happens is that I see in my fate cycle where you exist, you don't. So this is kind of it's. I have given a lot of thought about this particular thing. So these three cases are there, and whatever the quantum mechanics book you are reading, um, if you find that these three pictures are enough to explain all kind of measurement theories and all these kind of concept that came. I've not gone through details of the literature and try to prove it because in my lifetime I wanted to finish how to build an artificial brain. So this figure 4.1 is about understanding the very well-known quantum mechanics that you know very well, but you rewrite it in terms of geometric musical language. So what happens? Why do you want to do that? Because if you do it, then you can easily find out that if you have nested universes, then quantum mechanics is not so good. You need to go beyond quantum mechanics, and you need to add some more features to explain that kind of system, and and then we can build it up. For an example, figure 4.1b. Here we have quantum interference source and quantum beating. So quantum interference source is, you can see that we take a circle always, okay? As I said, wave particle theory, wherever you like a circle, and you try to push the circle through two holes. So through two holes it goes, but the circle also expands, and then it covers the other boundaries also. So it creates a host, big host circle, and then a guest circle, and then you get the original circles that is coming up. So three kind of circles actually come out in a quantum interference experiment. So one particular thing you might have noticed, that when you have the biggest circle, the host, that is actually the entanglement. So one light sources, when it is divided into two circle, it becomes, then on a big host circle we put one circle, so it goes, and then, or two circles we put on a big host circle, we put two. So basically one phase cycle actually regulates the two. So when you come to geometric musical language, what happens is that you give a physical picture to the entanglement, which in normal equation based practice of quantum mechanics, you don't do it. You don't have any expression. As I said that, as we said many times, that we follow the Feynman's dream, or many people who advocated geometry dynamics philosophy, that everything in the universe is a geometric shapes. And as in 1962, Feynman said that one day we will have a science when geometric shapes will change, and then that would explain the physical principles. So there will not be any equations. Instead of equations, we should draw pictures, and then everything would change by itself, and that would be the true picture of nature. So we have tried to do that throughout this book. We have tried to respect that, and as much as possible. We are not saying this is the absolute, but without any doubt, this is the first attempt to actualize their dream. So now what happens, entanglement, you get a host circle, and then you guessed those who are entangled, and then you get the one reality, it comes the small tiny holes, small two circles, those are the system points. Now what you get is, if you have this kind of situation, then you get um, a big circle and another small and another one. So that can represent the whole event that happened. So our objective is to represent any event in terms of circles or clocks or periodic. So what happens in case of non-periodic event? We say that in non-periodic events is not understood properly. If non-periodic events, all the situations are taken, then you will be able to find some part of it. So if you take a very large circle and then small circle one, you will always find linear events or some non-linear features, random features. But when you put a big circle and that, you can recreate that kind of small localized non-linear parts. So it is not that we are rejecting the aperiodic events or something like. Aperiodic events could be represented as in terms of nested circles. There is no problem in it. Anybody with a little bit of programming language can do that. So we are not getting into that kind of debate. So what happens is that in figure 4.1b, you see that how the fractal interference would look like. So it means that in case of fractal interference, what will happen? In this quantum interference, when three circles are coming out, you will find that because of the symmetries, they will create a fractal features. Fractal features means triplet of triplet or doublet of doublet. This kind of features will come because of the phase prime metric that we described in chapter 3. So what will happen is that there will be a group of groups. So they will group based on the symmetry of the circles and the singularity points that you will encounter, and other things would happen. So in the simple quantum interference sources, it will not happen. But if you pass it through a material and that is spiral, and then there has vortices like structures where geometric phase could be integrated, then you will find the existence of fractal interference. We will show experimental evidence in which system you can find the fractal interference. It is not that all systems will exhibit that, but many systems would. So in quantum beating, what happens is that it is almost similar to quantum interference, but here what happens is that your two holes by which one circle divides into two holes and then comes up, then the diameter of them are a little different. So the circles of different diameters are created. So what happens is you can't convert the host guest system into one integrated circle like you did in quantum interference. So what happens, the two different are dissimilar, so you cannot couple them into one. So in the host, two guests remain, and then the difference of them comes up with a normal beating. But in fractal beating, you will have much more number of groups or circles. So basically, the difference between quantum mechanics and then fractal mechanics is that you allow fractal mechanics, you allow much more integration of circles, guest host systems ad infinitum. So there is no limit. In quantum mechanics, you have a limit, one or two, so three layers of clocks. That means at any given point of time, your reality have a host, you are part of a host, or you have a guest. That guest, you don't see it, it is in the infinite world, and from future it is affecting your present, or something in the past. At present it exists, and in the past there is some change and it is affecting your present. So that is the maximum situation you can imagine in a quantum mechanics scenario. But in the fractal mechanics scenario, you have a present, and then you have a future, you have something, some past, but the past also have past, and that past also have something, and then future also have some future, and then future. This is ad infinitum. Now what happens, there's a new kind of mathematics and algebra that you need to build, that which part in the future universe will be affecting this one, and who will be, and it is not random. It has a very delicate mathematics, and we build it. And that is the beauty of fractal mechanics. So it is for a different kind of system. It is a system where you have event inside event inside event inside an event, but at the same time you can have it could be reduced to quantum mechanics also. So it is not rejecting quantum mechanics in any way. It's a generalized mechanics, and quantum mechanics is, so when you delete all the clocks, keep only 3. The present, guest, and a host. And number C, figure 1.1c, creation of a system point. So normally, in atoms, you have ground level, you have excited level, energy goes up and energy goes down, and then it can go up and down, up and down, up and down many times. And then you can have a circle, and then you can imagine a system point which is causing the periodic motion. If an energy is trapped in a cavity, it goes up, collides with the surface, and then comes out, down, goes up and down, up and down, up and down. Then you can also consider a system point. And then another very, very interesting thing is host counts is a pixels rotation. It's the bottom part of figure 4.1c. So when you see that, you'll find that the pixel side, pixel circle, if it is similar to if a new clock is added, which is regulating the motion, the phase motion of a clock, and then its diameter, its clock diameter is similar to the pixel diameter. So pixel, you always have a pixel, right? Pixel clocks are there, discrete cycles, and then it exists after every finite uncertainty, after every uncertain time of Planck's time. After every Planck's time, this small circle moves, goes, it exists there, and then it exists there. Probability of finding it is very much next point, next point, next point, next one, next one, next one. Come here. Now, if you have added a circle, if you have the ability to do that, you just create a system point. So this is how you can create a system point. Then figure 4.1d, the birth of quantization. Quantization is the same thing as I said, that the earlier used to consider system point as a point. In the fractal mechanics, there is nothing called a point, because everything is a point, and the point, it cannot exist in fractal mechanics, right? Because in GML also cannot exist, because you have a circle, and circle, every pixel of the circle is made of some small circles, and then you go to that circle perimeter, and then those perimeter, all the pixels are made of some other circles. So nowhere point we cannot put. It just stops you going bottom. So point is actually a restriction. The definition of point in the existing definition of geometry and is a restriction that doesn't allow you to move downwards, and then straight line is a restriction that doesn't allow you to go upwards. So both straight line and point, it doesn't exist in GML, doesn't exist in this book. In the Nanobrain book, we cannot consider a straight line or a point. It will be very, very difficult, because it stops your journey, because you have to go freely upwards and freely downwards in different imaginary worlds. Though the book is restricted in 12 to 20 different dimensions, 12 to 20 times icosahedron geometric shapes, because we think more complex geometric shapes is not necessary. With this, we can explain all other dimensions. We can restrict them into icosahedron and dodecahedron, say 12 and 20, and then we can manage with the smaller dimensions to explain the other one. And because of Plato's rule that if you know up to icosahedron, dodecahedron, octonian, and quaternion, and then you don't need to know much. Topologically, you can explain at least with 86% to 99% efficiency. You can recreate the universe. Not fully, it is impossible. By our own phase prime metric, it is impossible to learn everything about the universe. But a large statistics, large part of it, you can understand. So then we come to figure 4.1e, coherence. So what is coherence? So coherence is 3 cases are there. You see cross, and then right. Right one is you have many clocks, and then all in the same phase point. Okay, circle, same point. If one system point is a little bit here and then other there, then if they move and then if they rotate, then they are not coherent. So coherence you can rewrite in GML very simply. So I hope that you find it very interesting. You can do it by yourself. You take out the quantum mechanics textbook, and then you take a paper and a pen, and you go on writing all the principles that you knew about the quantum mechanics, Schrodinger equation and others. Schrodinger equation, we have done it very nicely, and you will see how beautifully you can write them, and you can explain what will happen in different cases. You don't need to write equations or other things. So that's the beauty of GML. And then that's why chapter 4 for me is the most beautiful chapter in this book, because it doesn't create much pressure on you, just like unlike chapter 2. And another thing is that mm, at the same time you can relearn everything that you learned before. So you will see that what you learned before remains intact, and but you can get much more insight into the system. So fractal, in case of fractal coherence, what will happen is first of all, it could be symmetry. That means suppose in case of quantum coherence, what you do is in circle, 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 and you have dot, 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 dot. Okay. Now, what you do is in case of fractal coherence is that you have a circle, and then some kind of nested circles are there, but globally it looks like a triangle. And you have another geometry, a circle, and only 3 circles are there. It also looks like a triangle. So this triangular symmetry is similar. So it could be a fractal coherence. So the possibility of coherence in quantum mechanics is only one. But in fractal mechanics, when you go, then because of geometric self-similarity, also you need to see the rotational direction based, and then topologically, and then similarity of singularity. So there are many different ways you can build coherence, and then you go on generating phenomena. So in that sense, from quantum mechanics compared to quantum mechanics, fractal coherence is much more richer, and then it gives you lots of freedom to build new theories and new systems. Figure 4.1f is what do these fractal mechanics come from? So quantum mechanics, we know that we have a ground level, it goes to atom, goes to higher level, and from higher level, when it wants to come to a metastable state, say, then it could have infinite different kind of states, many. And that actually energy levels are very closely spaced, so closely spaced that which level it is coming from the excited state to the metastable state, you cannot determine. When you cannot determine, you get quantum mechanics. So basically what you do is you allow the system to vibrate in such a way that you create you take one energy state and you split it many energy states, and very closely spaced. So so if sometimes you may ask that, does it always have to be the Planck's constant and all these things? Actually, what happens is, in the true quantum mechanics, you can observe when Planck constant comes in. So what happens is your time and energy is such that even at the atomic or molecular level, you can see that where it is coming, which level it is coming from, you cannot understand. So what you do is you create a Hilbert space, and then in the circle, you have another circle which is very hazy. Means you have big circle, and this small circle that is there, that is the excited states energy levels, and the diameter is very hazy. Diameter could be very small and then very big. So a domain is there, a circle diameter, below which its diameter could be anything. Okay, so that's how you can rewrite the origin of Hilbert space in which is very well known for many years in quantum mechanics. You can rewrite it using GML, geometric musical language. Now, what happens if this highly dense energy spaces are not homogeneous? They are inhomogeneous. So many spaces are there, and they are symmetrically connected and coupled. So what will happen then? then you will need fractal mechanics, because what will happen is that there could be some metastable states and others. So you go to much hard, much complicated time domain where you need to rewrite the Hilbert space not as a circle, but that circle is like a singularity point. You enter inside, you find circles, and then many circles connected, and then a topology of clock. So that topology, when you try to explore that one, you come to fractal mechanics. Then figure 4.1 G. In G, fractal harmonic oscillator, just like quantum harmonic oscillator, you know that in the quantum harmonic oscillator means at 0, 0, you will get a peak, energy peak. And then it will not be like classical mechanics where outside you have the highest and then lowest. But fractal mechanics is not about where is the highest and where is the lowest. Unlike quantum mechanics and classical mechanics, the kind of debate that you have been reading for many years. Here, it's a composition of patterns. There are certain points which are allowed by prime symmetry in nature, where you see around peaks, and then somewhere you don't see the peaks. So it's a composition of peak distribution. So there could be features like classical, that there is a distribution of peaks like the classical, and then you will find at certain cases small peaks are there. So what happens is when we come to fractal harmonic oscillator, we basically consider there is a very fundamental symmetries that are governing. That's the prime-based symmetries in the universe, and then that actually comes. That actually is very explicit in certain mechanical systems. So there, fractal mechanics is essential. We just can't go for quantum mechanics, which is very homogeneous in the uncertainty region. So exploring uncertainty or exploring confusion is all about GML, right? So that's why the GML is very useful in understanding fractal mechanics, not the equations. Okay. So figure 4.1H. Now what happens is entanglement. So what you do is suppose you have a circle, and then you have all homogeneous things. Okay, so that was kind of situation in fractal mechanics in the entanglement. So one circle, and then there are many circles, identical diameters and identical system bonds, identical pixels, and all these conditions are satisfied, and then the symmetry are also identical, and then you say that it's a fractal mechanical entanglement. Now, what happens in fractal mechanics? They are connected by fundamental symmetries and the prime symmetries and other kind of topological symmetries. When that also comes into effect in doing entanglement, if those parameters are not related, uncertainty regions are very homogeneous, then of course you go to quantum mechanics. But if it is not homogeneous, because you see that Planck constant is the only constant that you are thinking that it is the lowest level, and then orbital energy is very close, and then all are homogeneous. But what if I create similar situation at the very classical domain, where you energy density are such that your system cannot access it? So you are now considering in this universe that all those energy levels in the atomic orbitals, I cannot. But in future, you can have a technology where you can see what is happening. But who stops us building new experimental systems where you have almost homogeneous distribution, but there are those hazy regions of energy levels are actually coupled with each other? Then what happens in case of when you are linking this kind of integration or coherence or entanglement with the symmetry of the primes? If you break the entanglement, spontaneously this entanglement could rebuild. That is figure 4.1H. That is the beauty of fractal mechanics. So you can see that other kind of symmetries have coupled entanglement. So you break one kind of entanglement, other kind of entanglement was holding the information. It comes back and regenerate the entanglement that you are seeing over there. So in quantum eraser experiment, you have seen similar kind of situations, but this is very natural in case of fractal mechanics. Okay, so it is not a very big deal in case of fractal mechanics. Then figure 4.2b, figure 4.2a. So what we see in the Hilbert space, we have classified what are the unique features of the Hilbert space. So Hilbert space could be oscillating time cycles. So basically, Hilbert space in case of quantum mechanics, it's a sphere inside which you cannot look. So it has infinite states on its surface. And then you can only access only after entanglement. You are able to detect who are there, but that Hilbert space could be oscillating. That means it could have in the infinity. It could change the infinity point. I have discussed in details in tutorial 2 and tutorial 3, in chapter 2 and chapter 3, explaining chapter 2 and chapter 3, that infinity, when you send it to infinity, the phase prime metric, when it sends to infinity, you can mathematically actually show this. I mean, it doesn't require much. I mean, Ramanujan did it, that he just shifted the infinity point little, and then they created sum of all the natural number integers is minus 1 by 12. You can do many such series and many things. He was the first, Ramanujan was the first to demonstrate it, but he was not the last. There are many other people who created many such infinite series, and then they showed that infinity gives back unique things. But what happens is that this infinite space is actually changing following a very particular pattern. Then it will return to you in the reality, different ways. So that oscillating time cycle, and then indefinite diameter counter. So simple clock, time crystal, 12D bidding. So these are kind of features that you can have in the Hilbert space. And time crystal means, as I said, that you consider that all the energy levels that are very densely packed energy levels. When system degrades from excited state to the metastable state, you can't tell where it is coming from. That is the very fundamental origin of uncertainty that we where Planck constant could exist. But those energy levels could be integrating with each other with 12D different dynamics. So 8D dynamics, 10D dynamics, or 20D dynamics, and holding topological information, and nothing can stop it. So these are the kind of situations where that you deal with in fractal mechanics. And then fractal condensation. So is in 4.2b. So in fractal condensation, what happens is that two or more locations undergo simultaneous condensation. So normally what happens is that in quantum condensation, like Bose-Einstein condensation, you have integral spin particles, and they come together and come to single energy state. So all of them come to single energy state, and not exactly single energy state, but all the energy levels it vibrates are all like very closely spaced. So even though Bose-Einstein condensate, say 80,000 atoms come together, and then they create a single energy level or single energy state, or the ground state. But it's not absolutely the ground state. Okay, always in quantum mechanics, it says that you have very closely spaced energy levels. In case of fractal condensation, in a fractal world, in that energy level, there are many energy levels which are integrated with each other topologically, and many different relationships exist in the Hilbert space. So what happens is that many imaginary world where I am, and then inside me, and inside me, and inside me, and above, they can undergo condensation simultaneously, because this imaginary world could be coupled to this imaginary world, and that coupled to another one. So when this one and this one comes to same state, other one is affected. Then that one comes and the other is affected. So it's kind of a chain reaction. It could be cyclic. It's affecting all others, and then infinite loop is running, changing this kind of condensation behavior. So this we call fractal condensation. Again, if you consider three imaginary worlds, one the reality that we have in the past and the future, and then you can get back to the quantum mechanics. So origin of uncertainty is plenty in fractal mechanics, self-assembly of quark, 3D projection from 2D topology projects into infinity, and then it comes back, and then there are many things. And how do they originate? So when you rewrite the phenomenon of quantum mechanics in terms of geometries and the phase prime metric, then you will find that, and a lot of other ways, the same event that you know in quantum mechanics can happen in many different ways if you include phase prime metric and then geometric musical language, because of geometric restrictions and flexibilities that geometry allows or topology allows. And then phase prime metric has a pattern of primes, and then that also has lots of dynamics here, original dynamics hidden in it, as we described in chapter 2. So both of them would play together to generate origin of uncertainty. But it is not that you can't explain. It is just that you can explain topologically, and with the symmetries. You cannot have a straightforward linear rule that you know very well in the equation based science. So then D figure 1D, how the wave function, Schrodinger's wave function, everybody knows. Finding a particle, it has a probability distribution, and now you can have, if you have a particle and then you want to find somewhere, in case of fractal mechanics, what will happen is certain features, actually you will find the probability of finding it is here much more, and then certain features here, certain features there, like certain set of symmetries, when it will be interacting, you are seeing it with certain set of symmetry, you will find it here. But if you're seeing it some other symmetries, you'll find it there. If you find with some certain pattern of clocks, you are reading that kind of that wave function, then you will find that it takes the shape of your structure. So in this way, psi could have many layers of integration, just like phase prime metric. And then you can have a different morphogenesis forms that you can see. So wave function in fractal mechanics has multiple system points, 4.1e if you go, and then Hilbert space morphs part by part. So they change its shape, and then they relink. It could be, it's just like a living life form. Entanglement forms and disappear and reconstitutes in case of fractal mechanics. You just can't have entanglement is broken, so broken forever, and then you can't rebuild it. So you have to create a new system. No, you can break the entanglement and rebuild the same entanglement, because other kind of entanglement are in place because it's a fractal mechanics. So so it is while doing quantum mechanical experiments, many people reported similar kind of things, and actually we consider those results as also as proof of quantum fractal mechanics that we are proposing. We are saying if you start writing it in terms of geometric shapes and others, and then you will start seeing it. So symmetry of prime position, and then coherence forms and breaks in constituents. So all these are kind of typical features of the wave function in fractal mechanics. So psi is not psi anymore. Psi is much more like a living life form. And then F is with number, you get prime factors. So now what happens is earlier in the fractal space-time, those people who wanted to go beyond quantum mechanics, many people have tried to go beyond quantum mechanics. We are not the first one. But what they try to do is to change the space-time curvature. So now we have a space-time topology prime. So we will not discuss it in details in this book. We will write a separate book for that. But just to tell you that space-time and topology means GML, geometric musical language, and then PPM, phase prime metric, the chapter 2 and chapter 3, those parts also come in the space-time. And then you can have fractal mechanics, and then you can have nested Hilbert space and all these kind of typical features of fractal mechanics. And then you will get a new metric. So like Schwarzschild metric we used for astrophysics to create the create different phenomenon of the universe. We predicted many phenomena using space-time metric. Similarly here we will take a space-time topology prime metric, and then we will recreate the universe. Mm. So, so this is the kind of figure 4.2, and then we go to figure 4.3. So, uh, in case of fractal mechanics, in case of quantum mechanics, if noise arrives, then what happens is that if there are two systems quantum mechanically entangled, quantum mechanically entangled means the Hilbert space or the highly dense energy levels here and highly dense energy levels there, um, they remain over there. If some reason noise comes and from highly dense energy levels it falls down to lower level, uh, and doesn't come back actually, it remain over there, then entanglement breaks. But in case of fractal mechanics, what happens if there is an entanglement, and then entanglement may break but it can come back, because you can take the noise and can jump to other kind of symmetries. This particular type of entanglement is broken, but other kind of entanglement is there, and then again you bring it back to the similar kind of entanglement. So and the creation of virtual clock. So basically, you can have um, you can have two different kind of systems whose symmetries are self-similar, and then what you can do, you can create a virtual clock. You can regenerate it, not just by cooling temperature, but by other kind of conditions like symmetry of primes, topological self-similarity, and then of course the energy level, density of energy level is one of the factors, but there are other factors with which you can recreate the wall. And then in room temperature also you can regenerate quantum entanglement between two systems, just like it happens in optical systems. People do it regularly, but you can do it with much better control. Figure 4.3b is creation of singularity. So what happens is uh, mm, how the singularity happens here. So you have a nested sphere, a time crystal, and then it goes inside the pixel. Going inside the pixel, every time I'm saying pixel, oh, no, what is that? Suppose you have periodic events, and then state by state, there is a time gap. It should not be the Planck constant, but there could be other kind of constant also, which can let you moving through a cyclic state. Now, what happens is the time domain during which you will find that a particular pixel exists or a small time cycle exists. If you have a clock architecture, time crystal architecture, universal time crystal architecture, as we said, that we do not follow the Wilk-Jacks time crystal definition, or the Arthur Winfrey's time crystal definition, because they use only one clock. We use clock inside a clock inside a clock. So it's a universal time crystal, we say. So if we can put that inside the pixel, how do we put it? The whole time domain of operation should be less than this pixel, then it will automatically go. So in the temporal domain, we don't need to take one thing and then go there and then put it over there. No, if temporal matches are there, it's automatic. So we have given a new mathematical operation, we have named it, and then we apply it. So singularity, figure 4.3c, singularity could be space-time singularity you can find in black hole, and then you can have winding number singularity you can find in quantum mechanics continuum. You can have block point and magnetization singularity, you can find it in magnetic bubbles. Dielectric permittivity, it goes to infinity. In hyperbolic metamaterials, you will get it. So singularity is not just one type of singularity phase goes zero. It happens many places in the field of physics, and many places it was reported. We have compiled it in a small table in figure 4.3c, but this is just the tip of the iceberg. You can recreate singularity region in many different ways, clocks in many different ways, in many fields, in many systems. So figure 4.1d is actually, if you put a clock and then inside another clock, then if you see the classical waveform changes, you will find that there's a hunch as a particular phase. Okay, if there is a third one, then you will see more hunches. That is the classical picture of nested clocks or universal time crystal. But when you go figure 4.3f, so what happens when you have intermediate sources, intermediate energy levels, or higher excited energy levels with very high density of energy levels you can't differentiate? Then what happens due to the difference gap, you can have quantum beating, and then figure 4.3e, you can have one clock, and then in quantum mechanics, suppose this clock diameter is such that it is in the intermediate energy level. So what happens is the clock that you nest with it could exist here, 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 all around the perimeter. Isn't it beautiful? So you know this by, well, if you are a very ardent student of quantum mechanics, you do many mathematics, and then you do not fear mathematics at all in quantum mechanics, and you understand what kind of mathematics you are doing. Then you go back to your textbooks in good standard textbooks, and you will find figure 4.3e in a very complicated set of equations. People have philosophically tried to argue that when you are in the Hilbert space and you have a circle, then your the next clock that you add could exist anywhere on the perimeter of the circle. This is a beautiful simplistic presentation of huge mathematical discourse on quantum mechanics. And then what happens is that you will find that instead of one, you will get multiple peaks in the frequency spectrum, and then you will find waveform also gets peak at many different places. And then there could be time 3, that is you have a Hilbert space, and then you have a Hilbert space, many, and then you have a Hilbert space, many. And then what happens is that you get a very complicated features. So universal time crystal in fractal mechanics actually gives you wide ranges of peaks in the FFT spectrum if you do the measurement, and it creates due to uncertainty many kind of new peaks which you cannot explain in normal kind of quantum mechanical measurements. So you can get a fractal behavior of self-generating resonance peaks continuously coming where you don't know, because you are operating inside the uncertainty space, uncertainty space-time topology metric. Sorry. Figure 4 point, we come to figure 4.4a. Figure 4.4a, again the same picture, that if you want to create what should be the energy. So how do you say the energy is changing? So that means basically you have a host clock, many glass clocks. So if number of clocks increase, and then this symmetry also increases, then you say that your energy is increasing, and then if it decreases number of guest clocks, and then you say that it has decreased. Now, if clockwise and anti-clockwise rotation also changes, and then also the energy could change. So what figure 4.4b is, who makes the pixel of clocks? I explained it many times, why I don't know, but again it has come back that inside a pixel you put a world, and if you to go inside and take one of the clocks, and then you go inside, you find the pixel. So classical mechanics, quantum mechanics, and fractal mechanics, if you just compare 3 of them, you can find simply what I have told many times, that basically you go inside the Hilbert space and then you create many things. But one thing you have to consider always, that it's not the Planck world where we have to go always and then do it, because that's the quantum mechanical part of it. But it has another beautiful aspect to apply in classical mechanics. And what is that? That you don't use h as Planck's constant. There's some other constant is there, which actually regulates the uncertainty in a given system in a very classical domain. So h is, instead of h dimension of h is an action, and then you can change it. So figure 4.5d is actually a chart that action, Planck's constant is action, so it doesn't have to be that level. So you can have different time domain, different action, which is actually regulating the uncertainty of energy and time in that particular system. And what you can do, you can harvest it and you can apply fractal mechanics. So figure 4.5d is the most important table in this book. So what happens is you remove the taboo that h is the only limit in the universe. There cannot be any. You can construct systems where you can construct this kind of small constant, which will regulate the uncertainty and of energy and time, angular momentum and velocity. So all these kind of uncertainties you can create, and then using that, what you can do is you can in that particular time domain, so in one time domain you just restrict it, and inside that, so you can create singularity, and inside that another singularity of another Planck constant, inside that another universe with another Planck constant. So it doesn't have to be Planck constant, but just Planck constant like action and other parameters. So that actually would give you how to reverse engineer a nested imaginary universes, or a system that will exhibit fractal mechanics, or artificial brain. So in case of artificial brain or other kind of systems, we are saying that you need nested universes, but figure 4.5D is the guiding principle for any physicist that he would follow. Now figure 4.5C, so you can rewrite electromagnetic interactions, different fundamental forces in terms of circles, GML, which is very easy. You can redo it if you have a standard elementary particle physics books. Just go there, and then you will find it very easy, very easy. The way they have worked in this particular field of elementary particle physics, they have contributed so fundamentally. The group is a group of 12, and group of 3, group of 5, I mean color code, and with quantum chromodynamics, and everywhere that drawing the same phenomenon, and them in terms of circles or GML is not a very difficult thing to do, and you can apply PPM also. Let me know when you do it, these fine things. I did some, but because the book is about artificial brain, so I cannot describe in details those things, but definitely you will be able to see some more things in the coming days. Figure 4.5b is important. So figure 4.5a is actually how do you do it? How do you use elementary particle physics, and then you regenerate, redefine mass in terms of GML? Because if GML is there, everything, as I said, that every single thing in the universe you have to represent in terms of clock, nested clock or circles. So so mass, you cannot reject mass also. So so you need Dodecanian metric, but anyway, we will get back to that in some other book, some other time. But we are saying that GML and PPM must express everything. The concept of space, mass, and the material we sense in figure 4.5b. So you have when observer fails to become a pixel in the host, it becomes a space. So just remember figure 4.1b, what you saw, observer and observed, you are redefining, right? So if your clock is there and the clock is host and it's comparable, it doesn't become a pixel, and then this new clock that comes doesn't make this one as its pixel, so it becomes very big and it's pixel there. It does not happen, then you get space. So those are comparable, then you get the different space. And when the observer is morphed, then it becomes mass. So that means when you have many and the clock have so many pixels, that and the observer when it sees it, and those small pixels or temporal time domains actually modifies this observer, and it is not able to get into in any of its diameters. Okay, then you cannot take the observer and put it inside this clock, so you make the density of the pixels too much. So what happens is it cannot go there, it gets modified if you go there. So in this kind of scenario, or nested, if you need at least 12 imaginary world to explain in GML to explain mass, because 2 into 2 into 3, 2 into 3 into 3, 3 into 2 into 2, this kind of triplet is a must. So what happens is that when you have a high density of pixels, then it can stay in multiple different states. They can group those pixels, and then the pixels of your observers thing is actually modified, because they morph each other, satisfying a condition. Then you say it is mass. It's little difficult. It will not be required much, but we just wanted to say that you can do many things with this GML. Then figure 4.6. 4.6 is a chart where in terms of primes we have represented the fundamental constants of the universe. The reason is different. Actually, this kind of fundamental constants are very close to the to reality, and what you do is when you there is a difference between primes, pure primes, and then the fundamental constants. But actually, we can create a geometric series, as we explained in the chapter 3, that you can create infinite geometric series, which could where the critical topological constraint that happens if you want to generate those infinite series, those actually give you the fundamental constants. So we have seen it in many cases, E pi phi, and then their correlations, and then there are multiple fundamental constants. You can bridge them. Actually, you get other fundamental constants. So you will find that they are all related to fundamentally few number of infinite series. According to us, it should be around 12 to 15 number of infinite series, and they will interact with each other, projected to infinity, and comes back, and then you get an infinite series that is actually the fundamental. So each fundamental constant is an infinite series. I don't know why that is not taught in the textbook, but every fundamental constant that you see in the universe must be an infinite series, because according to GML, because phase pi metric, when it projects to infinity, multiple different topological series, and then topological constraint comes back, but a topological constraint comes back, it is also an infinite series, and that's a fundamental constant. Figure 4.6 6a is microtubule. Figure 4.6 is experimental evidence on microtubule that it follows fractal mechanics, not the classical or quantum beating. So basically, what happens is you go to figure 4.6b. So normally, if you have a optical axis and extraordinary axis, then light comes and it splits into two parts. So if you have if you have a monochromatic light that is coming, and then you will find that a different polarization and this quantum entangled sources are created. So microtubule is also known for birefringence. So that means if you send a monochromatic signal, it will split into two different quantum coherent sources. It will naturally build, and that's why we pumped microtubule at different frequencies. You can see in 4.6b, and then we measured standard quantum electron flow-based quantum interference patterns. So when microtubule is electromagnetically resonating at particular frequencies, then you can find that at certain points, at certain cases, it almost looks like we got in 24.91 megahertz. At 00, you find that there is no black dot. So if there is a black dot at 00, it's a classical interference, and if it's a bright point, it's not. So basically, our result for microtubule was that it is very difficult by sending electron to create quantum entanglement inside the microtubule. It's just impossible. That's why when we design the brain and then others, we send monochromatic light, and optical and magnetic vortex comes out of the microtubule, and then those vortices actually can entangle. So inside using flow of electrons or flow of ions, it's impossible. So that is kind of quite certain. But there is something very interesting in figure 4.6g. You will find that we were testing with gate bias, source bias. We were testing the energy levels, and then we are doing the DIDV, or the quantum interference pattern. We zoomed at a particular part because patterns were something different, and then we found that there are circles and circles and circles and circles. So it's just like a circular loop-like. So inherently, even if you supply electric field and electromagnetic fields, microtubule has the ability to create electric or electronic vortices also. So optical vortices we know, or magnetic vortices we know, but even the electron flow actually in the differential spectrum, you can resolve that the the electron density distribution is in a cyclic phase. So it's just like electromagnetic field is coming, then it is rotating, just like optical tweezer and other kind of thing. So inherently microtubule has this particular property, and that fractal features tells that it is a primary candidate of exhibiting fractal mechanics. The figure 4.8 is actually figure 4.7 was about microtubule, but figure 4.8 is a system that we designed and synthesized in our laboratory. We call it PCMS, palm dendrimer based molecule. And then figure 4.8a is actually showing you that CWS, combined excitation emission spectrum. So what happens in horizontal direction, you change the input light frequencies, and vertical direction is emitted light frequencies from the system. And you find some peaks are there in 4.8a, and those peaks actually tell you where which orbital energy levels are actually exchanging energy and who are participating. And we zoomed a particular part continuously, and we found more and more energy levels. So this is what we predicted in fractal mechanics, that you go to two energy levels, you go to one energy level where the interaction is happening, and then you zoom it and you will find some more energy levels are there. So this is the first and the direct evidence. In 2014 we published these experimental results, and then we never understood that we invented a new kind of mechanics that is far beyond quantum mechanics, and it is the example of fractal mechanics. Much later we understood it, and then we explained it in figure 4.8b. All these pictures are taken from the book, and then we created series of topological structures, and we published it, I think, 2015 in a separate paper, figure 4.8g and h, where we created series of different kind of symmetric structures. And during synthesis, actually fractal mechanics was governing the synthesis. We also reported it. We reported all the features that we have included now in fractal mechanics, but that time we absolutely didn't have any idea. So fractal mechanics ends here in figure 4.8. Figure 4.9, when we go, then we find that what we do is we need to write clock, and then computation mathematics would happen naturally. So in this chart, you will find how to write, how do we write 2, 3, 4, 5, 6, 7, 8, 9. So 2 means 2 singularity points connected by 3 means 3 singularity points, 4 means 4 singularity points. And then phase change is equal to the space. So you see, the first top left figure panel is there, that d theta dt, so you have one host circle and two circles are there. If rotations are not similar, then you get rotation is in the same direction, you get plus x, negative direction you get minus x, and x means the difference between the system point, that is the x what is showing. But if system point is not there, then it's guest and host, and it is 1. So system point, when system point would not be there, when it is not required, when both are moving in the same direction with the same angular speed. So so x, how we write it? We write a circle, and then we put a small dot, not on top of it, just little beside. So clockwise is plus x, minus x is anti-clockwise. You can change it also. And the system point, as you know right now, is the phase singularity. And if if x carries a hidden pair of variables, then you know, you do xy, you do x to the power y. So when power, it goes up, and then it creates something. So we have defined how to define number systems, and there, how to write it in 10 to the power 2, how to write 3 to the power 2, and how to write continued fraction, how to write fractional number, how to write imaginary number, how to write rational numbers, irrational numbers. All these lists are there in figure 4.9. And figure 4.10, actually, how do you do the addition, subtraction, multiplication, very basic elementary mathematics. Okay, how do you do it? So you take a geometric shape, and then simply taking geometric shape, you can do even the continued fractions. All these things you can do. And figure 4.11 is actually partial differential equation, integration. How do you do it? So you draw the pictures, and then you can do this kind of things. Laplacian equations and all very basic elementary mathematics that you used to do in your school days. Actually, you can do again. Figure 4.12 is actually we insert a new symbol. It's like, in pi and then in the middle, and we call this the simple. What it does is, if you want to do multiplication, then take a circle and insert. So split the gaps is division. So if you have a gap, split it, we'll get division. So in geometry, you don't need to understand what complex things you do. You do not need to put the number of the integers. In using GML, what you do is form closure, complement, transfer. This is a table in figure 4.12. And in this table, actually, you follow what we are asking: repeat, transfer, reduction, fusion, split. And then you get the mathematics done. So what you do is you follow all these steps. But all these steps you can follow. You can look at the time domain, and naturally it will get selected, and mathematics would go on. Whatever mathematics is required. And so basically, CFGA operator, we call it. It's a chi-like function. And then 1, 2, 3, 4, 5, 6, 7, you saw 8, 9, 11, 10, 11, 12. That means actually the steps that are there. So they are all integrated, and chi actually naturally could build mathematics. Another very important feature of this fractal mechanics is duodecanian algebra. And how do we come to duodecanian algebra? Octonian, you know, and in figure 4.13, actually we tell you how to do duodecanian, how to write duodecanian. Duodecanian was never written. This is the first time in the world in the last 200 years. Nobody tried to go beyond octonian, but we have gone to duodecanian, and we have already published paper to go up to icosanian. So that means up to 20 by 20. So here 12 by 12 and 20 by 20. When you go to 12 by 12, you will find that there was a phenoplane using which people used to solve how to find the multiplication table. So if you want to invent a new algebra, you need to build the multiplication tables. The other things are very easy to do: addition, subtraction, and so if you do multiplication, then that's the same way to do division. So you need, if you want to invent a new algebra, you need to redefine a new kind of addition, subtraction, multiplication, and division. So multiplication table, that's why is considered the most supreme to invent a new kind of algebra. So we created a duodecanian algebra, and we made this multiplication table. While making the multiplication table, we found that phenoplane is not helpful anymore. You need to create 11-dimensional manifold. And how to build that manifold, we have drawn it here. And then you can have multiple coexisting solutions simultaneously. So you can group them and you can build them. So there is a local symmetries of the tensor term inside the tensor terms, which comes into effect. So duodecanian algebra now, there are extended, very extended 30-page, 60-page papers that we have published. But here in this book, we just introduced the new concept that has been used. So what happens is we go to the figure 4.14, where we have shown projection from infinity is actually how it works. How to do it. If you have a piece of paper and pen and you are drawing it, how can easily you build it, and what are the equations? We come back again, 12 equations, and these equations actually we get because of the topological projection to infinity and getting back from infinity, and then quaternion, octonion, and duodecanian, they work together. So when we build the brain, so quaternions, octonion, and duodecanian, they work in different phases of the brain in a very unique manner. The next figure 4.15 is about how many different spirals are generated. So E by phi only take 3 fundamental constants and one equation. So in the previous figure 4.14, you saw that e pi phi square plus pi square equal to pi square is a fundamental entity. And we have explained only one entity here because in this book we cannot, because of the volume constraint. And we want to cover the entire artificial brain construction, so we cannot go. But just for e pi phi, you integrate many different kind of resonances. And then the beauty of it, figure 4.15e is actually fractal space-time. And when you come here for fractal mechanics, is actually e pi phi means magnetic resonance, mechanical resonance, electrical resonance are with a certain ratios. So figure 4.15f is actually a plot of how different resonances are integrated, and when those resonances are integrated, a spiral motion is generated. That is explained in figure 4.15a, figure 4.15a, and then figure 4.15b, and many different examples of different kind of creation of different kind of vortex or vortex motions. Figure 4.16 is actually a summary of this chapter, that how this algebra is different, and fractal mechanics and geometric fractal mechanics and geometric algebra, how they are correlated. So this actually ends the chapter, and today we have covered a couple of things. We have covered how using geometric musical language we can rewrite quantum mechanics, and while rewriting quantum mechanics we understand that geometric constants and then primes, the pattern of primes, when both come together, we cannot keep the Schwarzschild metric or other kind of metric for artificial intelligence or natural intelligence. We need to bring new metric. That we have published now, and then we need a new mechanics because different imaginary worlds are interacting. So you saw that in Dodecanian algebra, different part of the imaginary world, 12 imaginary world there, 12 imaginary world here. When we are doing the multiplication table, then we find that that imaginary world will interact with that imaginary world and affect over here. So it's a beautiful composition of different kind of imaginary worlds together. So two major things. That is, when you have imaginary worlds nested inside each other, you need new mathematics, new way of doing it, and you need a new mechanics. So not mathematical algebra, new mechanics, new metric, and then you need projection to infinity, and getting back from infinity, the fundamental constants will come and they will regulate the systems. So fundamental constants may appear as if they are not related to primes, but fundamentally they are related to primes because they are governing primes, density of primes, and all these features of primes that are described in chapter 2 is actually governing the geometric sets. They're restricting geometric sets to change in a certain manner, and then that actually generating the fundamental constants. So here in this book, because we are concentrated only on making artificial brain, we will be using only those features, certain features which would be necessary. So next time I will come up with a new tutorial for chapter 5, where we will be describing incredible features of this kind of computing before we enter into the final. So today we finished mechanics and mathematics. We have new language in chapter 2, and then new metric, phase pi metric in chapter 3, and now new mechanics and new mathematics, new algebra. We call it Dodecanian algebra. Though Icosianians are there, but we have not detailed much in this chapter. It is just a summary of how to do it. Thank you very much for listening. I will come back again. Thank you.